Why should a magnet deflect a mercury jet? Mercury isn't magnetic, but it will conduct electricity. This jet bends because we're passing an electric current along it. Conducting fluids bearing currents in magnetic fields can behave very differently from non-conducting fluids. Magnetohydrodynamics, or MHD for short, is the study of these motions in the case where the fluid can be treated as a continuum. Most of the universe consists of ionized gas, a conducting fluid, and MHD dominates astrophysics. These solar flares owe their strange form to magnetic forces. Ionized gas exists on Earth, too. But on Earth, there are also conducting liquids, such as the acid in this battery or the mercury in the jet. The field is horizontal, the current is vertical. Deflecting the jet, there is a force perpendicular to the current and the field. The precise statement is that if the vector J is current per unit area in the fluid and B the field, the force per unit volume of fluid is J cross B. Here is mercury in a flat pipe. Between these electrodes, we're passing a vertical current. When we bring the magnet up, J cross B causes pressure changes which pump the fluid. In this experiment, we impose currents from an external source. But motion of a conductor in a magnetic field can induce currents, and these too produce J cross B forces. As the ring crosses the edge of the field, it links an increasing amount of magnetic flux. According to Faraday's law, a current will be induced around the ring. This current produces the force we observed. The J cross B forces on a conductor are distributed throughout its interior. When the conductors are solid, it doesn't deform. But what happens with a liquid? Here is mercury in a shallow trough, and this powder will reveal the motion. The effect of the J cross B force is obviously much more complicated for a deformable fluid than for a rigid solid. So, we must examine carefully how J cross B is distributed and how it affects each individual bit of fluid. In order to see how the fluid moves internally, we use this flat duct in which we'll put a transparent electrolyte. The duct goes in a magnet that provides a uniform vertical field. Here is a cross-section of the apparatus. This inclined mirror enables us to view the fluid in the direction of the field lines. In this view, we can see two electrodes, between which we can pass a two-dimensional current distribution. The resulting J cross B distribution is quite complicated. The pressure difference between these 2 points will be revealed by this manometer. Now the fluid is in, and the upper fluid in the manometer is colored to provide contrast. The fluid in the duct is stationary and contains dye lines. The magnetic field is on, but the current is off. Now we switch on the current, and the manometer reveals the resulting changes in pressure. But the fluid in the duct moves only slightly. In this case, then, the fluid can sustain J cross B forces without being seriously disturbed. The pressure must have changed, so so that the pressure gradient balances J cross B to a close approximation. But the pressure gradient is an irrotational vector, and so we conclude that here J cross B is irrotational and is not capable of making any fluid element spin, even though it is very non-uniform. Now the fluid is in motion. When the same J cross B distribution is applied, the manometer indicates that J cross B forces are again altering the pressure distribution. But for a given flow rate, the flow pattern is unaffected. J cross B is still irrotational, and changes in the pressure distribution are able to balance it. So far, the currents have been in a uniform magnetic field. Let's move to the edge of the field. Now the currents cross the region where B falls from a uniform value to 0. Here's the electrolyte at rest. The current goes on. Let's repeat that. J cross B is rotational now and makes the fluid spin. More precisely, it creates vorticity. The J cross B distribution is like this, falling off rapidly in the edge region where it is rotational. But a pressure gradient can only be irrotational, so it can't balance J cross B anymore. And the fluid can't stay still. Now let's see the effect of the same J cross B distribution when we have the fluid flowing along the duct. To see this, we move downstream beyond these dye injectors. This is the flow without the current. Now we switch on the current. The flow contains vorticity. It is generated upstream at the edge of the field by those rotational J cross B forces. Here's the previous experiment again for comparison. So the important question about J cross B in these experiments is whether it is rotational or not, whether it can change the vorticity. Let's look again at this mercury trough where the currents are induced rather than imposed. Vorticity is being generated, but these forces can sometimes suppress vorticity instead. Before we see this in a fluid, let's consider this metal loop, free to rotate. If we apply a magnetic field normal to the axis of rotation, the motion is strongly suppressed. It's easy to see why. When the loop is aligned like this and rotates a little way, it begins to link magnetic flux, and the current is induced like this. The resultant J cross B forces oppose the rotation. For small inclinations, the opposing torque is proportional to angular velocity. If the axis of rotation is parallel to the field, there is no opposing torque, because the loop doesn't link a changing magnetic flux. But rotation stops quickly when the axis is perpendicular to the field. So, in a fluid, a magnetic field should suppress vorticity whose axis is normal to the field. Here is a trough of mercury in the gap of a magnet that can produce a horizontal field. Vertical vortices will be made by dragging this blade through the mercury. They are made visible from above by reflecting a pattern in the surface of the mercury. Here there is no field. Here it is again, and in the lower picture, the field is on. The vortices decay faster in the field. Let's repeat that shot. Here, we're outside the field. And now the blade enters the field, which is stronger than before. The J cross B forces never let the vortices get started. They reappear as soon as the blade leaves the field. We've now seen rotational J cross B forces creating vorticity and suppressing it. But something else happens in this annular tank, where the vorticity originates at a moving wall. Across the gap, we can apply a radial horizontal magnetic field. Now we put the mercury in. To reveal vorticity, we have this free arm which tethers a float. The paddles of the float are free to rotate with the mercury and so reveal its vorticity. After the mercury reaches a steady state of clockwise motion, we can see that the vorticity is anti-clockwise, as we would expect. But watch what happens when we put on the field. There. Here's the motion again without the field, and it goes on now. The float has the same angular velocity as the frame holding it, so most of the mercury is now rotating like a solid body, slipping over both cylinders. Actually, the slip occurs across thin viscous boundary layers called Hartmann layers. With this mechanical analog, we can see what happens. We spin the loop without the field. When the field comes on, induced forces act briefly until the loop moves like this. There is now no change in magnetic flux linked. There is pure rotation, just as in the mercury. In the flow without the field, the vorticity is such as would cause a loop in the fluid to link a changing flux when the field comes on. So J cross B changes the vorticity to avoid this. As we repeat the experiment, observe the direction of the vorticity. With no field, it's anti-clockwise. The field makes it clockwise. The J cross B forces have also produced intense anti-clockwise vorticity in the thin Hartmann layers. So here, J cross B has rearranged the total vorticity, not suppressed it. We've now seen that magnetic forces can drastically alter a fluid motion, but motion of a conductor can alter a magnetic field, too. The induced currents produce their own magnetic fields, which must upset the original field to some extent. These nails follow a field line. Watch the field change as the loop goes by. This perturbation of the field was a weak effect in all the experiments so far, and we ignored it. But when the induced fields are too big to ignore, an entirely different kind of MHT occurs. To understand this, let's look again at that rotating loop. The induced current creates an induced field, which combines with the original field to make the total field less inclined to the loop than before. The point to notice is that the field is perturbed in such a way that the rise of flux linked by the loop is reduced. If we stop the loop rotating, its resistance causes the induced current and induced field to decay, and the total field relaxes back to its original form in a time that depends on the ratio of the inductance and the resistance of the loop. This is the magnetic relaxation time, which gets longer as we make the resistance less. The extent to which a rotating loop perturbs the original field depends on how this magnetic relaxation time compares with the time for a revolution. Here the relaxation time is the shorter, and the field continually relaxes back to its original form and is hardly perturbed. Then the magnetic forces are dissipative. There's only a torque when the loop is moving, inducing a current. But when the magnetic relaxation time is long, because the resistance is small, the field is deformed more and more, until there is virtually no change of flux linked by the loop. As we approach perfect conductivity, the induced EMF needed to drive the currents becomes negligible. Spontaneous currents alter the field so that the flux linked by a perfectly conducting loop never changes. Between these large field coils, there is a small coil. We're going to use it to show how a perfectly conducting loop would behave. The coil can be connected to a feedback system so that it always links the same magnetic flux. The magnetic needle tells us the direction of the field. Now there is no feedback in the coil, so when we turn it, the needle is not affected. Contrast that with what happens when the feedback is on. The needle stays in the plane of the coil because it perturbs the field so that it still links no magnetic flux. If the coil is displaced, it oscillates. The damping is due to mechanical friction. There can't be electric dissipation if there is perfect conductivity. It's less than the magnetic relaxation time, so the field is strongly perturbed. And now the J cross B forces produce a restoring torque, which, for small inclinations, is proportional to angle of inclination, like an elastic restraint. In a fluid, the same ideas apply. In any loop drawn in the fluid, the magnetic relaxation time is of order mu naught sigma L squared, which is big if sigma, the conductivity, is large, or L, the scale, is large, as it is in astrophysics. The question is how this time compares with other times characteristic of the motion. In this experiment, the magnetic relaxation time for loops drawn in the vortices is short compared with their rotation time. So J cross B is dissipative, not elastic. Before we show elastic behavior in a fluid, let's consider the simplest motion that contains vorticity. These rectangles represent layers of fluid which can slide past each other. There is then vorticity between the layers. Suppose we apply a magnetic field like this. The question then is, what will be the effect of the J cross B forces whenever they are elastic? Rather than dissipative. Consider this loop lying between two layers of fluid. At present, the loop links no flux. If we move this layer down, the induced currents around the loop produce elastic forces like this, tending to twist the loop back in line. This force pushes this layer of fluid down, and then the next loop suffers the elastic forces. And the action is passed on down the line. Here's a working model. On these pivoted rods are attached flexible loops which are connected to a feedback system so as to simulate perfect conductivity. With the field on, we disturb the first rod and the motion propagates as a wave. Here it is again in slow motion. So this model of a perfectly conducting fluid in a magnetic field shows us that the rotational J cross B forces cause the vorticity to propagate along the field lines as a wave. This kind of wave is named an Alfvén wave after its discoverer. Now let's see Alfvén waves in a real fluid. In order to approach the perfect conductivity condition, we have to use a liquid mixture of sodium and potassium, which has to be contained in this airtight tank. We also have to make the waves travel fast by using this magnet to provide a strong vertical magnetic field. Then, the transit time of the waves is short compared with the relaxation time of fields in the fluid. Inside this tank, we place this structure. We excite motions at the bottom of the liquid by passing a current radially through it, between this central electrode and this cylindrical one. The radial current interacts with the vertical field to produce J cross B forces that make the fluid swell. At first, only the bottom layer of liquid moves. The liquid above is at rest, so there is vorticity between it and the moving layer below. But immediately this vorticity must propagate away along the field lines as an Alfvén wave. The layer of radial current travels with it, too. The current layer deforms a magnetic field. We can detect the magnetic changes with this search coil, which is immersed in the fluid. The signals from the search coil are displayed on an oscilloscope. Now the apparatus is ready for our experiment with the tank in the magnet gap. These leads carry the exciting current. To get a good picture on our oscilloscope, we excite the waves repeatedly. Each wave dies out before the next is created. The upper trace shows the sudden onset of current in the exciting winding. The lower trace shows the signals generated in the search coil. Now the magnetic field is off, and the lower trace shows only some stray signals. No signal reaches the search coil itself, which is shielded by the liquid. But as the field comes on, the trace changes. This signal is due to the wave passing the search coil. This signal records the wave after it has reflected off the top. If the fluid were a perfect conductor, the search coil signals would be like this. The width of these ideal peaks is fixed by the size of the search coil. The resistance of the fluid makes the observed first peak broader and weaker. The second peak shows that the reflected wave is broader and weaker still. But we do see that even in an imperfect conductor, J cross B forces can act elastically enough to give propagation of vorticity. Vorticity has been our main theme because J cross B forces affect fluid motions by being rotational. They sometimes create vorticity, sometimes they suppress it. Sometimes they even reverse it. But when we approach the condition of perfect conductivity, the nature of MHD changes entirely. The J cross B forces act elastically, with the result that fluid particles can pass their vorticity from one to the next along the magnetic field lines. We've dealt only with incompressible fluids like mercury. Things get more complicated when the fluid is very tenuous or can change its density,